In the last lesson, we saw how we could use a circle in order to understand radian measure, which is a different way to describe an angle other than degrees. In this lesson, we're going to be learning probably the most important diagram in virtually all of mathematics, because this diagram, called the unit circle, is going to be able to be a quick reference guide, not to memorize, but again, to understand and visualize what's happening. It'll be a great tool to be able to quickly calculate trigonometric function values of all of the special triangles. You can see here are two special triangles. Now, I drew three of them just so that we could see from the horizontal that this is a 30-degree angle of elevation, a 60-degree angle of elevation, and a 45-degree angle. So remember, for a 45, 45, 90, the two sides, the two legs are identical. And by the Pythagorean theorem, the hypotenuse becomes root 2. For the 30, 60, 90, keep in mind that the longest side is twice as long as the shortest side, which is opposite the 30-degree angle. And when we calculate using the Pythagorean theorem, the third side simply becomes the square root of 3. Now we're going to do something kind of interesting here in order to turn all of the hypotenuses into a length of 1. So right now you should recognize that if this is a length of 2 and I want it to be a length of 1, then I need to shrink that triangle to be a similar triangle, same angles, but I want that to be half as large. So we're going to simply divide this by 2 and divide this by 2 and divide this by 2. And if we do so, we end up getting the side lengths that look a little bit different than they did before. With a hypotenuse of 1, we can see that the shortest side is 1/2 now, while the longest side is the square root of 3 over 2. Now, one thing to really recognize about these two ratios is that 1/2 is equal to 0.5, while the square root of 3 over 2 is larger. It's approximately 0.87, which is why this isn't too surprising when you look at the fact that the shortest side of 1/2 is in fact shorter than the longer leg of root 3 over 2. So you can see, because this is the same triangle over here, if I were to cut this in half to become 1, that would mean that this side becomes the square root of 3 over 2. And of course, the shorter side becomes 1/2. And now for this 45, 45, 90, same idea, but now we recognize that this root 2 has to be divided by root 2 in order to turn into 1. So if we divide this by root 2 as well, and divide this by root 2 as well, then we've maintained a similar triangle, but now the side lengths are going to be different. They're the same proportion, but they're a little different. So now notice, if I multiply the top and bottom by the square root of 2 over the square root of 2 in order to rationalize, the numerator becomes the square root of 2, and the denominator becomes 2. So that now the hypotenuse is still 1, while each leg is going to have a side length of square root of 2 over 2, and the square root of 2 over 2. Now, for the 45, 45, 90, you should recognize that both sides are obviously the same, but we want to be able to come up with a decimal approximation for this amount as well. And it turns out to be approximately 0.71. And I should say over here that this is approximately the same as well. Okay, well, that makes sense as well, because if the longest side of the hypotenuse is a length of 1, then that must mean that we should have a value of root 2 over 2 and root 3 over 2 and 1/2 that are all shorter than 1. And sure enough, each of those decimals are shorter than 1. So what I'd like to do at this point is use these values in order to come up with sine of 30 degrees and cosine of 30 degrees. And likewise, the same thing, I'd like to look at sine of 60 degrees and also cosine of 60 degrees. And not to say the other four trig functions are not important, but right now the sine and cosine are going to be the most important for this diagram we're about to create. So the first thing to recognize here, I'm sorry, this should be 45 degrees. So the first thing we should recognize is that the ratio for sine is always y over r, and cosine is always x over r. Now let's look at the benefit of making the hypotenuse 1. If the hypotenuse is 1, then that means that r is in fact 1. So it shows us that sine of 30 degrees is actually the same thing as just the y coordinate. And cosine of 30 degrees is the same as the x coordinate. Which is really, really helpful, because if we think of this as being our origin, 0, 0, then this would be considered my x coordinate, and this would be considered my y coordinate, where the hypotenuse is equal to 1. So now, without having to really do much work, we can see from our special triangles that sine of 30 degrees is our y value, or 1/2, while cosine of 30 degrees is our x value, which is longer, and therefore the square root of 3 over 2. So if we take a look at 60 degrees now, keep in mind again that sine of 60 degrees must be the y coordinate. For a 60-degree triangle, notice how the x coordinate is small and the y coordinate is large. So that must mean that the small value of 1/2 is going to be the x coordinate, or cosine, and the y coordinate will now be root 3 over 2. So based on our cofunctions, this should make sense that cosine of 30 gives us the same value of sine of 60. And cosine of 60 should give us the same value of sine of 30. The one that's different over here is sine of 45 degrees and cosine of 45 degrees. But notice that because these x coordinate for a 45-degree angle, the x coordinate and the y coordinate are the same, now we just have to realize that sine of 45 is the square root of 2 over 2, and cosine of 45 is also the square root of 2 over 2. So this is nothing new, because we've seen this before. We've calculated all of these using reference triangles. But now we're going to come up with a nice, simple way to be able to recognize what these sine and cosine values are on our unit circle. Now let's take a look at this on the xy coordinate plane. So if this is our y-axis and this is our x-axis, let's assume that each of the points that are on our x and y axes are 1 unit away from the origin. Then that would mean that this point out here would be 1, 0, and therefore 1 unit away, and all of them would be 1 unit away. So now let's take a look at an angle theta. Let's just draw it in the first quadrant. So at this given angle theta, notice that that angle intersects the circle at some particular point in the xy plane. More specifically, it would have this x coordinate, and it would have this y coordinate. So if we want to determine what that point on this circle is, we've got to realize that this hypotenuse is 1 unit long. So if this hypotenuse is 1 unit long, then why don't we try to find what our x and y coordinates are? So this is our x coordinate, and this is our y coordinate. And therefore this point is the point x and y, which is not really too big of a surprise, except for the fact that now we see this triangle with a hypotenuse of 1. So let's try to find sine of theta and cosine of theta on here. So notice the cosine of theta is adjacent over hypotenuse, or x over r. And so x over r in this case is just x over 1, which is x. Which means that if we force the triangle, or if we force this circle rather, to have a hypotenuse of 1, the x coordinate automatically tells me the value of cosine theta. So if we want cosine of theta, we're just going to need to look at our diagram for the crossing point on this circle. And likewise, if we take a look at sine theta, if we force the hypotenuse to be 1, since we know that the ratio is y over r, then sine of theta is y over 1, and therefore y. Which means that the y coordinate on this new diagram is simply sine of theta. And this is an extremely important idea for trigonometry. That if we could force the hypotenuse to be 1, which is the radius of this circle, then what we've done is found out what the x and y coordinates represent. They simply represent cosine of that angle and sine of that angle. And it doesn't matter where the angle is. If we were to go all the way back here and draw this new angle, then that angle would have a crossing point on the unit circle up here, again, of cosine of that angle and sine of that angle. So to see the significance of what we've just learned, I have here the circle that we had on our last lesson that shows the degree and radian measurements for all of the special angles in this rotation. Now you can see within each circle, or I'm sorry, each quadrant, there's a 30-degree angle, a 45-degree angle, and a 60-degree angle. So namely, even though we're labeling them on the outside of the circle, we should recognize that this angle right here is actually 30 degrees. And our next angle inside here is 45 degrees. And our next angle is 60 degrees. Okay. So notice that these actually do represent angles of rotation. It's just that we're writing the angles on the outside. And what we have here is another circle that's blank. It has all the same angles, but I deleted the angles so that we could write something else on this. But why don't we now assume that this length from the origin here at 0, 0 to the outside is 1 unit long. Well, that must mean that every one of these lengths to the outside of the circle is also 1 unit long, no matter where we go. So we should at least be able to come up with the points that lie on the axes themselves. So each of these points are actually going to be ordered pairs that are 1 unit away from the origin. So we should realize that on the positive x-axis, this point is 1, 0, and this point on the negative x-axis is negative 1, 0. And since the x coordinate is 0 up here, this is the point 0, 1, while this is the point 0, negative 1. Now what we're interested in is finding the rest of these points. What is this ordered pair, and this ordered pair, and this ordered pair? Because what we just saw is that if we could find out what those ordered pairs are, then we're going to know what cosine of those angles are going to be and what sine of those angles are going to be immediately, just by knowing the points on this unit circle. So this method is going to be a way for us to be able to find sine of 7 pi over 6, or cosine of 2 pi over 3, or sine of 7 pi over 4, without ever having to do any work other than visualizing this unit circle. So within each quadrant, we should see hidden inside a 30-degree angle, a 45-degree angle, and a 60-degree angle that are all part of these special triangles that we developed up top. So our 30-degree angle is the shallowest light blue one. The 45-degree angle is the one that's right in the middle, the red one. And the steepest angle, or the green triangle, is going to be the 60-degree angle. So by taking a look at this diagram, we should be able to recognize that if the hypotenuse is 1, then our short side is 1/2, our longer side is √3/2, and this is what we derive from our special triangles, which means that the crossing point of our unit circle is the x-coordinate of √3/2 and the y-coordinate of 1/2. But if you also take a look at the green one, let's take a look at the green triangle, which is the same triangle, just tilted up on its side. Now I should see that if the hypotenuse is 1, then the short side is now 1/2, and the long side is now √3/2, which now means that the only difference is the x and y coordinates have flipped. So we have 1/2 √3/2 for our 60-degree angle, and √3/2 1/2 for our 30-degree angle. So the way to remember this is just to remember that √3/2 is larger than 1/2. So the larger side is √3/2, while on this bottom one, the larger side is √3/2. So now for our 45, 45, 90, we can see again that the hypotenuse is forced to be 1. If you've forgotten why, that's because we have chosen our radius to be 1 unit away from the origin. So if the hypotenuse is 1, then we learned at the top special triangles that this leg is √2/2 and this leg is √2/2, which now means that the x and y coordinates here are the same, √2/2 and √2/2. So now that we see how we can construct this one quadrant, we're now able to recognize that I could find all of my values for cosine and sine simply by looking at the x and y coordinates. We just need to remember that x is cosine of theta and y is sine of theta. So if I want to find the cosine of 30 degrees, I simply look to the x-coordinate, it's √3/2. And if I want to find sine of 45 degrees, I'd simply look to the y-coordinate, it's √2/2. And if I want to find cosine of 60 degrees, I simply look to the x-coordinate of 1/2. But this doesn't only work for the triangles, it also works for, let's say, sine of 270 degrees. Well, remember from our diagram here, the 270 degrees is straight down. So we would look to where 270 degrees is. Sine of 275 degrees is the y-coordinate. So we would know that sine of 270 degrees is -1. So with this one single quadrant that we've created for the unit circle, we're going to be able to find the rest of these because they're identical. You should recognize that this triangle is identical to the one on the first quadrant. And so is this triangle. And so is this triangle. All of the triangles are identical. They all have a hypotenuse of 1. They all have the same exact adjacent and opposite sides. So the only differences here are going to be the signs. And so notice that as we continue to move our way around, the signs here in the first quadrant are obviously positive and positive. Positive x's and positive y's. But when I move back into the second quadrant, now we've got to realize that I've moved back for the x direction, but still up for the positive direction. So all of our x values are negative, all of our y values are positive. Likewise, back here, we can see that we've moved in the negative direction for x and the negative direction for y, going down into the third quadrant. And lastly, over here, I can see that we have a positive direction for x and a negative direction for y. So the way that we can see this, and we'll just do this for one of these, let's just say that we draw this triangle. This is obviously going to be a 2π/3 angle based on the fact that we're at the 120 degrees. But if I wanted to find sine and cosine, I just have to reference that same exact triangle in the first quadrant. Notice that the x coordinate is small, so it's 1/2. The y coordinate is large, so it's √3/2. And therefore, the point is going to be 1/2 for x, except that it is -1/2. While the y coordinate is still √3/2. And notice that the ratio doesn't change, only the signs, which means when we come down to this 60-degree reference angle, again, the short side is 1/2, the long side is √3/2, but the signs are different. I've now gone back 1/2, and I've gone down √3/2. And lastly, in the first or in the fourth quadrant, the y or the x coordinate is 1/2, while the y coordinate is -√3/2. So now I see that the ratios that we're using for all of the green triangles, all of the 60-degree reference triangles, are identical. So no matter what pi/3 angle I look at, whether I look at pi/3 or 2pi/3 or 4pi/3 or 5pi/3, cosine of those pi/3 angles will always be 1/2 because it's the short side on the x-axis. The only difference is whether or not it'll be positive or negative. So now let's look at the 30-degree reference angles, or the pi/6. We could see between the green and the blue here, the only difference is that the x and y coordinates have flip-flopped, which again makes sense if I were to now draw the other triangle in this quadrant. Now I can see the shortest side is the y coordinate, so that's 1/2. So therefore, this is going to be √3/2 first, but it's negative. And 1/2 is now second. So we can see that the x's and y's flip-flop between those two values. Going back here, I went back further than I went down. So negative √3/2, and now -1/2. And finally, on the other side, we've gone a positive √3/2 because we've gone to the right, and we go down -1/2. And lastly, the easiest one, in fact, is going to be the 45-degree reference angle, or the pi/4 reference angle, because the x and y coordinates are always the same. They're always this value of √2/2. So if I look at √2/2, that's now going to be upwards, and a positive √2/2 because I've gone up. And now both values are negative in the third quadrant, so negative √2/2 and negative √2/2. And finally, positive √2/2 going forwards, and negative √2/2. And what we have just created by taking all of these points along with their corresponding angles is what we refer to as the unit circle. Many people try to memorize this unit circle. I think that's a really poor choice of study technique. I think the better choice is to understand and recognize the patterns. So as we saw in the last lesson, all the pi/6s are going to be the ones closest to the x-axis. So those are your 30-degree reference angles. All of the pi/4s are going to be halfway into each quadrant. So those are your 45-degree reference angles. And all of the pi/3s are furthest from the x-axis. So those are going to be all of your 60-degree reference angles. So if we now want to find either cosine of an angle or sine of an angle, we can do it by simply referencing this unit circle. Now, just to put in perspective what each of these particular ratios are describing, remember that in terms of least to smallest, we could list our smallest value that we see on this unit circle of 0. And we can see that the largest value is, of course, 1. Okay, now in terms of absolute value, I could go into the negatives as well, but let's just look at, say, the first quadrant. Okay, so we can see that the y coordinates go from 0 up to 1. And so let's just take a look at how those change. So as we're moving around this circle, the angle is increasing So notice how the y coordinate is getting larger. So the next value then is 1/2. It's the y coordinate of 1/2. Well, that must mean that this value right here of 1/2 or 0.5 is actually a physical y value on my y-axis. As I continue to move myself up this way, I can see that the next y value is √2/2, which is why this y value is √2/2, which is a physical location on my y-axis. It's approximately 0.71, and that's why in order, my next value is √2/2. And the last thing to recognize as I continue to move from √2/2 from 45 degrees to 60 degrees, the next value is √3/2, which means that my final value, my final ratio that I ever get to is √3/2. And I can see that that same thing happens when I end up going in the x direction. I can see that as I go from 90 degrees to 0 degrees, I can see that the x coordinate goes from 0 to 1/2 to √2/2 to √3/2 to 1, which is why as we move along the y-axis, again, this is 0 and this is 1, which is why this value on my x-axis is √2/2 and √2/2 and √3/2. So we should see that there's only really 3 ratios that we have to remember in order to find any trigonometric function on the unit circle. And these are the most special angles that show up regularly. So let's see how we could actually use sine and cosine. Since that's all the unit circle shows, how could we use sine and cosine in order to find the other 4 trigonometric ratios? But looking back to our proof up here, that cosine of theta is x over r and sine of theta is y over r. But if r is forced to be 1, then cosine of theta is x and sine of theta is y. So if we take a look down here now, we can see that cosine of theta is going to be our x coordinate on the unit circle, while sine of theta is our y coordinate. But notice that if we already know sine of theta and cosine theta, we know by the reciprocal identities that cosecant theta is the reciprocal of sine. So now we just have to take the reciprocal of the y coordinate. In order to find secant of theta, we simply have to take the reciprocal of the x coordinate. And since tangent of theta is equal to sine theta over cosine theta by using the quotient identity, I can see the tangent of theta is just y over x. So I take the quotient of the 2 ratios, or of the two coordinates. But if I look at cotangent theta, now I can see that it's x over y. So now, if we are given a special angle of 30, 45, or 60 degrees, or any of the reference angles in the other quadrants, all we need to find all 6 coordinates, or all 6 ratios, is the x and the y coordinate. So let's look at an example. Okay. Let's say we want to find the trigonometric function values of, say, 5 pi over 3. So let me start by taking you through my thought process. I am not going to draw the unit circle, but I am going to try to describe the process because I've never once memorized this unit circle, but I can understand where the angle is and be able to use that to calculate what the x and the y coordinates are. So let's first of all think about a pi over 3 angle, 1/3 of pi. So a pi over 3 angle is the angle that is furthest from the x-axis. So I know that it's a 60-degree reference angle. It's the steep angle. But 5 pi over 3 is a little less than 6 pi over 3. So we should realize that it is the steep angle down in the 4th quadrant. So I know that 5 pi over 3 is down here in the 4th quadrant. Now that I'm visualizing it being that steep angle in the 4th quadrant, the only thing I'm thinking of now is that in this triangle, which side is short. So at a steep angle, the x coordinate is short, the y coordinate is long. So that must mean that based on my unit circle, the short x coordinate is 1/2. The large y coordinate is √3/2, which is why we now can think through this without even looking at the triangle or of the unit circle itself, that for the steep angle of 5π/3, the x coordinate is short, so 1/2. And the y coordinate is long and it's going downwards, so it's negative √3/2. So notice that we don't have to draw reference triangles anymore. We don't have to convert this to degrees to be able to find out what that value is. We're just thinking about its location with respect to pi and noticing that once we have this, tangent of 5π/3 is going to be the quotient of sine and cosine. So if I divide negative √3/2 by 1/2, I now get negative √3/1, or rather negative √3. So now that I have all three of these, simply from our unit circle, we can now take the reciprocal of each. For instance, the reciprocal of cosine is secant. So secant of π/3 is 2/1. I can see that cosecant of 5π/3 is the reciprocal of sine, so negative 2/√3. But remember that we have to rationalize in order to put it in the correct form. And so cosecant of 5π/3 is negative 2√3/3. And lastly, cotangent of 5π/3 is the reciprocal of negative √3. So I see that that's 1/negative √3. So if I multiply top and bottom by √3/√3, then that gives me my cotangent value of negative √3/3. And notice that this would have been the same exact answer we got if we decided to use the reference triangle. For instance, if we go to 5π/3 and recognize that it is at 300 degrees, then I could draw the reference triangle, recognize that the hypotenuse is 2, the short side is 1, the long side is √3. I'm going downward, so it's negative. And then from there, we could actually use the reference triangles. But it turns out that the unit circle is a lot less work. You don't have to draw the diagram, and now you're just visualizing where that angle actually is. So now to revisit this proof that the x-coordinate is cosine theta and the y-coordinate is sine theta, let's now take a look at this triangle and recognize that by the Pythagorean theorem, x squared plus y squared is equal to 1, which should be kind of obvious for this circle because this from algebra is the circle equation where the radius equals 1. But the more interesting thing about this circle is that since we just determined that x is cosine and y is sine, for every circle where the radius is 1, we now have derived again the Pythagorean identity of cosine squared theta plus sine squared theta equals 1. So it's a surprising result when you end up looking at this triangle where the unit circle shows us the x-coordinate is cosine and the y-coordinate is sine. So the last thing I'd like to do is just be able to use our calculator to find a few values. So let's try a couple of examples. So let's use our calculator to evaluate the following here. If we want to find cosine of 1.85, remember what we do. We go to our calculator, we punch in 1.85, and then we get cosine. And we get an answer of 0.99948. I'd like to look at that for a minute and see if this seems reasonable. Okay, 0.99948. Okay. Well, let's take a look at our unit circle again. Okay. When I look at 1.85, we should think about approximately where that is. Remember that on when we're dealing with a circle, 1.85 is referring to the radian measurement. So I could see that one radius ends somewhere around here. So that's 1 radian. By the time I come back around again, another radian ends probably about right here. So this right here would be approximately 2 radians. Okay. So 1.85 radians might be somewhere around here. So remember, when we're trying to find cosine of 1.85, we're just simply looking at the x coordinate right here. And now the question is, does the x coordinate look approximately like 0.999? And the answer is no. So either our calculator lied or we did something wrong. Because notice that this x coordinate is 1, negative, and 2, it's nowhere close to -1, which is way back here. So there's a big issue here, and the issue is that cosine of 1.85 is not equal to cosine of 1.85 degrees. And our calculator is still in degree mode. Now that we've learned 2 different units of measurements, it's really important to make sure that we switch our calculator appropriately. So when I change this to radian measure and try that again, 1.85 is my radian measurement, and when I hit cosine, now notice that it's -0.27, -2.76. That makes more sense, that this value is -0.276, because I first of all recognize that on my circle here, it's going to be negative, and it's going to be somewhere closer to 0 than it is closer to -1. So keep in mind the idea of what a radian measurement is. It's mapping out the radius, wrapping it around the circle. Now let's take a look at cotangent of 1.3209. So notice first of all that there is no degree symbol. So I know that this indicates that it's a radian measurement. So I go to my calculator, and if I punch in 1.3209, I now want cotangent. But remember, there is no cotangent button here. So instead, we're going to have to do a little identity in order to change this. So let's first start off by changing this into 1 over tangent of 1.3209. The reason this is beneficial is because I have a button for tangent. So if we go back to our calculator, now I've got the radian measure of 1.3209, and there's my tangent value. Now I could go back and I could rewrite that 3.918 or so. So it's 1 divided by 3.918, and then I go back and I punch that into my calculator. But keep in mind that there is a button on my calculator to automatically take the reciprocal, which is right here. The 1 over x button will automatically make it 1 over that value. So when I take 1 over, and see what it did here, it's 1 divided by tangent of 1.3209. And so without having to punch that back in, I know that my value is approximately 0.255, and therefore 0.255 is my answer. So keep in mind that there's a big difference between radian measure and degree measure. And this extremely important circle is going to be your best friend moving all the way through trigonometry and calculus. So don't memorize it, but really try to look for the patterns that emerge as you look to the points and their corresponding angles. So because this is so important, I know that it's sometimes tough to draw this circle over and over. So there are all kinds of blank unit circles all over the web, but I'm providing this on my website so that you can actually print up a few copies and practice on your own. Practice the first time on your own, but if you have to refer back to the unit circle, then feel free. You could fill in the degree measurements along the inside track here where the degrees are. You could fill in the corresponding radian measurements closer to the edge of the circle, and then filling in each of their corresponding ordered pairs along the outside. Now, if you have to use your circle the first time to refer back to remind yourself, then so be it. But after 2 or 3 times, you should be able to fill this in relatively quickly without any help by looking at the patterns that emerge between 1/2 root 2 over 2 and root 3 over 2, as well as all of the radian measures that we learned in terms of pi.